In this video, I'm going to talk about whatever I remember after reading first chapter of Geometry of Physics by Frankel. So the first chapter, I don't even remember the name, but the first chapter basically talks about the idea of manifolds. Yeah, manifolds are integral curves. Just the introduction of integral curves. So the first half of the chapter is more or less getting us a bit familiar with the idea of manifolds, and for that the manifold this he talks about submanifolds of Rn, and by the definition I'm going to talk about later, Rn will be a manifold, and it will be quite trivial. I don't know if the trivial is the right word, but yeah. Now I will directly jump into the second half of the chapter and start with the idea of manifold. So, manifold is a set denoted by M, and we have manifold. This is a set, and we have patches. Yeah, he actually discusses a little bit about point set topology. I will go through those topics while I will introduce those ideas while I'm going through the idea of manifolds. So, I think I will leave them. So this is U. This is a open set on U, and associated with each patch we have a function phi of U such that it maps the patch U to an open set in Rn, because our manifold is of dimension n, and it has to have this property as well, that this is U, this is V, and this point this point, the common section of U and V, the common intersection of U and V. So if I take phi U of U section V, I will get this set, open set in Rn. Now if I take the inverse, and if I take now V, basically it goes back, then again comes here to V. I should get an open set. And what a great that's it. And when I mean U, I will leave that idea. It basically means when I'm defining a patch U with phi U, it just means this patch is locally homomorphic to Rn. That's what we mean when we say that manifold. When we look at manifold locally, it looks like Euclidean space, and in this condition of intersection of common part is the usual sewing part of the patches. That's all there is. Then he introduces us to manifold of projective line in R3. I think it won't be any useful, but it becomes useful when we study Mobius strip. And then what else did I read afterwards? This is the idea of manifold. Basically, this is the idea of manifold, and there is another theorem. There are two things. One is differential, and another one is submanifold using differential. And then there is the topic of vectors. Vector on manifolds. And is there any other thing? Then there is this. What's the name of it? I forgot the name of this. Integral curves. I don't remember the last section regarding the integrals curve where he straightened the flow. When we say diffeomorphism, will it suffice? Yeah, okay. So let's leave the projective line space aside. Now we have a manifold M and we have a function M such that it maps the M to N. So when we are going to say these M and N are when we are going to say the F is a diffeomorphism, the conditions are, let me remember, the conditions are quite trivial in fact and quite easy. Yeah, F should be continuous and differentiable. Yeah, F should be continuous and differentiable, and it should be 1 1 onto such that F inverse exists, and this F inverse should be in fact differentiable. Then only we are going to say F is a diffeomorphism from M to F, M to N. Now there is this idea of differential. Basically, differential is differential. So the idea is differential is we have a curve, we have a map from real number line to M, and so when we say is it M to I? Yeah, it's wrong. I'm thinking it's a mistake. It should be R M to I. No. It's R to M. You specify some point. It basically means we have a curve on U M manifold, and in fact it means this. Nah, it doesn't mean anything else. So you specify some number on the real set, and you get a point on M. So you basically get a curve. So what is special is that we have this curve, and suppose this curve is such that it passes through point P, at which the parameter of this phi is, let's say we say the parameter of phi is t. Then let's suppose it passes through a point P, and there's this there's another idea of tangent space. I forgot that also, and that also. Without it, I can't talk about differential. So tangent space, yeah, it will be introduced now. So this is phi t, and I have to get first vectors, and then I will get tangent. Phi t. Yeah, so we have a phi t, and at point P, the tangent is simply dx. The tangent will be d phi by d t or d lambda if I have used lambda as a fine parameter. Fine as a parameter, and then I use the chain rule d phi by dxi. So when I say xi, I basically means this patch. I'm using the patch phi u, xi dxi by dt. So what it means is dxi by dt d by dxi phi. Now what it does is there's a little bit more you can get involved in it a little bit more, but I will just leave it to here. We are going to associate one can show there is a one-to-one correspondence between a vector and the vector associated and the differential operator associated with the vector. So this is the differential operator associated with the vector, yeah, at point P. P and F has to be P. So this is differential operator associated with the vector. Now what I do is I define a vector simply by dxi by dt, where t is the parameter of this curve, and I use t by dxi as the basis. And there are a lot of ideas, there are a lot of confusion about it, and the main point is that we are not going to associate it any length with these vectors, and there's reasons to it. The main reason is to associate length to these vector, we have to get to the idea that it should be invariant whether we go from one patch to the other patch. Like if this vector lies in this patch, it has to remain invariant when we define it, whether we define it using u or define it using v. Alright, I will leave it to here. So vectors are associated with these, and these are called basis vector. Nothing so special. And the idea is that on the here we are going to define a tangent space. Tangent space is that the tangent in the manifold actually lives as in live in a home at a point P, not like in Rn where a real line or R2 on a coordinate space where you can translate them anywhere. So yeah, if you have to take it, if you want to add subtract those vectors, you can't do it because they live in a different vector space, which is called tangent space. And tangent space at a point in that book is denoted by using, I think, this point, this way. And the differential, the idea of differential is you have a function f, this one, f to m, and when I say this function f m to n, n has n coordinates. When I say it's a diffeomorphic, they will be different, and it has, let's take them different. So this function f consists of a set of functions which are x, y, and let's take a patch on y, n, and sorry, let me get it back, y, I, f, I, x, 1, x, m. Though I'm not caring about the indices whether they are up here or down here in this case. You should, I will talk about it later. So this I varies from 1 to n. These are a set of functions when I simply say f. So let's take f as a function from m to n. And what is special about it is, I forgot one more thing, and this is, I will leave it. F. Now you have a tangent, you take a point, you take a curve in M, and you define it at P. There is a tangent, and you are taking F. You operate F to this, and you want to see how this tangent is imaged in N. So for that we need a idea of differential. It's nothing so special. So you simply take f of phi t. Yep, that's all there is. And now we will be going to introduce the idea of, actually now you have to get the idea of, now I will talk about, sorry, I made a mistake back there. For vectors you need to get the idea of what is contravariant. But basically now if you take it differentiated with respect to t, you get, and use the chain rule, df by dxi, and am I doing it right? I think so. Dfxi, dxi by dt, where xi are the coordinates of the function phi. So basically, if I put some value of t, let's say 2, I get some point in m, and I'm taking patch u. So when I take patch u, I get n tuples or m tuples of whatever the case, whatever the dimension of the manifold is, and xi is that coordinate. So this is what we get. Now this f consists of tuples. I can use in fact y here as well. So yj dxi, and I should use total differentiation here. Yep, and this is some point in n y, so it is dy by dt, and here you see this is the component of the vector. So you see, if I use this linear transformation, it's a linear transformation, linear operator, so it maps vectors tangents in one manifold to another, which is given by f, and it's denoted by f star, and it's called differential. This